Welcome to our show. Today we're diving into a fascinating topic in space exploration. We've got an expert here to tell us all about something called the gravitational slingshot. So let's get started. Can you tell us what this is all about?
Absolutely. I'm excited to share this with you. The gravitational slingshot is a remarkable technique used in space exploration that allows spacecraft to gain speed without using fuel. It's particularly interesting when we look at missions like Voyager 1 and Voyager 2.
Wow, that sounds incredible. I've heard of Voyager before. Isn't it really far out in space?
You're right. In fact, Voyager 1 currently holds the record for being both the farthest and fastest spacecraft from Earth. What's fascinating is that it's even outpaced a more modern probe called New Horizons, and it's all thanks to this gravitational slingshot effect.
Hold on. How does an older spacecraft outpace a newer one? That doesn't make sense to me.
I know it seems counterintuitive, but it's all about how these spacecraft use the gravitational slingshot. To understand this, we need to look at how the Voyager probes moved through our solar system.
Okay, I'm all ears. How does this work?
Well, as the Voyager probes left Earth, they passed by several planets. Each time they approached a planet, they suddenly changed direction. Now, you might think they bounced off the planets, but that's not what happened at all.
They didn't crash into the planets. What stopped them?
Good question. When the probes got close to a planet, they were attracted by its gravity, kind of like how a magnet attracts iron. But because they were moving so fast, they were flung away before they could crash. It's gravity that plays the crucial role here.
Gravity, huh? I guess that's what keeps us from floating off into space, right?
Exactly. Gravity is the force that keeps us on Earth's surface. Without it, we'd be floating around like astronauts in space. When Voyager approaches a planet, it's caught by the planet's strong gravitational pull, which changes the probe's direction.
That's wild. Is there an easier way to picture this? It's a bit hard to imagine.
Sure. Think of it like the Olympic sport of hammer throw. Imagine the planet as the athlete and Voyager as the hammer. Gravity acts like the chain connecting the hammer to the athlete.
Oh, I can picture that. But wait, doesn't the athlete spin around a bunch of times?
Good observation. While the athlete spins several times before releasing the hammer, Voyager makes less than half a turn around the planet before being flung away. But here's the key part. Voyager speeds up during this process.
It speeds up. How does that happen if the planet isn't spinning faster?
The speed increase isn't because of the planet's spin. It's because the planets are already moving quickly in their orbits around the sun. When Voyager comes close, the planet's speed helps pull it along, making it go faster.
I'm trying to wrap my head around this. Can you break it down even more?
Of course, let's use another analogy. Think of the planet and Voyager as two marbles. The planet is a big, heavy marble moving very fast, while Voyager is a small, light marble moving slowly. When they meet in space, the big, fast-moving marble influences the smaller one, causing it to speed up.
Ah, that makes more sense. But where does all this extra energy come from?
Great question. The energy actually comes from the planet itself. When Voyager is flung away, the planet also experiences a tiny change in speed. But because planets are so massive compared to spacecraft, this tiny loss of energy is practically unnoticeable.
Fascinating. So, if the planets weren't moving, would this still work?
No, it wouldn't. If these planets weren't rapidly orbiting the sun and instead stood still, there would be no gravitational slingshot effect. The planets need to be in motion to transfer energy to the spacecraft and make it speed up.
This is mind-blowing. It sounds like a really useful technique. Do other spacecraft use this too?
Absolutely. The advantages of the gravitational slingshot are so significant that almost all modern spacecraft and probes try to use it. It not only increases speed, but also saves fuel. Scientists often call this the gravitational slingshot effect because it's like a spacecraft is being flung forward by a cosmic slingshot each time it passes a planet.
That's amazing. But wait, you mentioned earlier that Voyager is faster than newer probes. Why is that?
Right, let's take the example of New Horizons. It also used Jupiter for a gravity assist. However, it still didn't surpass Voyager's speed because New Horizons only had one gravity assist from Jupiter, while Voyager had two, one from Jupiter and another from Saturn.
Oh, I see. But why didn't New Horizons visit more planets like Voyager did?
It's not because scientists didn't want to, but because they couldn't. When Voyager was launched, scientists carefully chose a time when Jupiter, Saturn, Uranus, and Neptune were almost aligned. This allowed Voyager to visit them one after another, like stringing beads on a necklace.
Wow, talk about perfect timing. Does this alignment happen often?
Actually, it's incredibly rare. After Voyager's mission, these planets moved out of alignment, and such an opportunity won't occur again for hundreds of years.
That's incredible. So, even though we have more advanced technology now, we can't beat Voyager's speed?
Exactly. While newer probes like New Horizons have more advanced technology and leave Earth faster, they can't perform multiple gravity assists in quick succession like Voyager did. This is why they haven't been able to surpass Voyager's speed, despite being launched much later with more advanced technology.
This has been absolutely fascinating. Who knew that old spacecraft could teach us so much about speed in space? Thank you so much for sharing all this incredible information with us today.
It's been my pleasure. The universe is full of wonders, and the gravitational slingshot is just one of the clever ways we've found to explore it. There's always more to learn about space exploration.